to the cloud. You can turn on your video whenever it is required. So I started recording, and you cannot see my video. Let me start my video. Okay, so welcome to the second week. In the first week, we have done a general introduction to the electrified vehicles or vehicles in general, because first we try to understand the application, the requirement of the application, and why this application is important. So we start by defining what is an electric, what are the requirements for vehicles, and what are the requirements for vehicles, and we just made an introduction to the history. So what I can suggest is please watch all the videos, lecture videos, and try to follow what I do explain, because the topics are not complicated. The problem is the topics are new to you. So therefore, it will be good that if you can follow the lecture with me. So in the beginning of week 2, actually, we are going to learn some interesting stuff. We are going to understand how we need to decide on the size of the plant or the internal combustion engine or the electric motor in an electric vehicle. And later we will use this information to understand how much battery we need to install on the vehicle. So we are trying to understand the longitudinal dynamics, so the forces acting on a vehicle, so that how much force I need to generate with my electric machine. First, I need to understand the behavior of the mechanical system so that we can decide on the power and the speed characteristics of the electric machine. So therefore I will start by looking to the car. I will just share. We will start looking into the car like a black box. So we will just start from very outside. Assume that we have a vehicle and it is a black box. Now we try to understand once this vehicle moves at a given speed or at a given condition, what are the resistances associated with this motion? So we will start from the very outside. We will see the car as a black box. Then we will just go in to the different components and how we decide on the different components. So in the second week, our first lecture, today I'm going to do just 1 hour lecture, is on the longitudinal vehicle dynamics. I will also define what is the longitudinal vehicle dynamics and which aspects we are going to consider. So the content of today's lecture is here. I will talk about like one slide, vehicle requirements. Then you have a vehicle, what are the requirements of this system? Then we will talk about vehicle movements, vehicle resistances, and we will finally have a look into the dynamic equation of a vehicle. So we try to understand vehicle as a mechanical load to our electrical motor in long term, of course. So when we buy a vehicle or when we design a vehicle or the passenger vehicle, depending on the application, the requirements may change. But in this course, mainly I'm talking about the passenger vehicles that we use. What we know is we think about the performance of a vehicle. We have some expectations from the vehicle. As a passenger or as a user, we have some expectations from a vehicle. Also, as a car manufacturer, you have some expectations, requirements from a vehicle. So here there's some list. I will talk about them. The first is the performance. So it should perform. The performance of a vehicle is it should drive at different conditions. Then emissions, it should be environmental friendly. Comfort, so you are going to sit into the vehicle, so there it should bring you some sort of comfort. Security is quite important, and it should be secure way of transportation. Of course, then you need to pay some money, the initial cost and the fuel economy. Here, I didn't just put the fuel economy, but the initial cost too, because as you know, a vehicle can have a very good fuel economy, but maybe its initial cost is too high. So we need to think of both aspects at the same time. And the design, how it looks, because we are going to define our stuff with our cars, and visibility of the external environment. So this is how you can see the outside. So the windows, the front window, side windows, back window. So how you can see the outside, because you can design the best vehicle in terms of the performance and the security, But if I cannot see what is happening outside, then I have a problem as a driver. So the visibility also very important. When we come back to the performance, what we expect from the performance is we usually, when, for example, you get a car, one of the first things that you check is its maximum speed. So even if you can reach the maximum speed or not, but you check the maximum speed. The second one here is the gradability. Gradability means that if there is a high slope, what is the maximum slope that you can get climb? This is the gradability. Acceleration time is what if you just put full gas, how much time will it take for you to accelerate from 0 to 100 kilometers per hour? Or their second acceleration criteria, it is from 60 to 100 kilometers per hour. So in kilometers per hour. And as you know, the electric vehicles are proud of their acceleration time. So that's why they advertise themselves with the acceleration time. Drivability, so if you can drive the vehicle, so if you can take the curves, if you can control the vehicle and so on. Then lateral dynamics and vertical dynamics. I'm going to show that in the next slides. So the vertical dynamics is like the suspension, suspension is the correct word. Suspensions, how the vehicle is going to move in the vertical direction, vertical dynamics. Lateral dynamics, how the vehicle is going to move in the sideways, so the lateral dynamics. So these are important, especially for the safety and also for the comfort of the driver. Moreover, the range is quite critical for electric vehicles. So if we were talking about a combustion engine vehicle, we wouldn't put here the range. But when we talk about hybrid electric vehicles or electric vehicles, then we need to talk about the range, especially important for the electric vehicles, and charging durations is another criteria from an electric vehicle. So it means that when we design a vehicle or when we buy a vehicle, then we need to just make sure that it is drivable, its dynamics are good, it can climb a given grade, we can reach a maximum speed, and it gives us a good acceleration time. So previously I was talking about vertical and lateral dynamics. So here you see again the vertical axis in the here. And here is the longitudinal axis. This is the direction of the vehicle. And this is the lateral axis or transfer axis. So the mechanical engineers or vehicle engineers, let's call them like that, they work on both the vertical dynamics and lateral dynamics. But in this course, all we try going to look into is the longitudinal dynamics. And because we don't care about the suspension or we don't care about how we are going to get the curves. In this course, we all going to think is all the roads are straight. And we will just look into the longitudinal dynamics because we care about the fuel economy. And we try to understand how much energy we need to travel from point A to B. And we're just going to look into the longitudinal direction. So just the car is going to move forward in our analysis. So it means that we are going to look into longitudinal dynamics, forward or backward. It can be both direction, but just on this axis, we are going to look in terms of this course. Anyway, the other axes are not our topic. For example, here there's an example of an electric drives. Here, if you have the suspension and active suspension, you can change it with an electric motor. And in this case, you can really get good dynamics. But as I said, this is a different topic. And you can also watch this video later, maybe just I open it. Maybe you have seen those videos before. But you cannot see my screen. Anyway, at the end, maybe we watch that video. It's too late. Okay, great. So maybe at the end, if we have time, we can watch the video or you can just check it yourself. So here it is related to the both vertical dynamics and also, of course, by the lateral dynamics of the vehicle. And you put here these active linear electromagnetic motors. So as I said, we are just going to look into the longitudinal forces. And the longitudinal forces are the forces happening on this axis, on the longitudinal axis. In this axis, first of all, what we have is the aerodynamic drag. So if you try to move in the air, and we are all in the air, it means that we need to move the air. And due to this, that the air has to be moved, we are going to have an aerodynamic drag. This is the first part in the longitudinal axis. And the other axis is the rolling friction. So we know that the rolling friction is lower than the regular friction, linear friction, I guess. Regular friction, but still we are going to have some friction on the wheels. And the rolling friction is going to be just in the direction of the braking force. So it is going to behave like a brake. It is going to be just in the reverse direction of the motion. Assume that we are driving in the forward direction. And the rolling friction is just going to be in the braking force. So it is trying to stop our vehicle. Grading resistance, we will come to that later. It is if you want to climb a hill or upwards or downwards, or if you go down from a hill, if there's a sloped road. So it means that there will be some extra force acting on the vehicle. And this is the grading resistance. This can be positive or negative. Tractive force, it is just shown here, the motive force. So this is a real wheel driven example, most probably. So that's why the motive force is just applied to the wheels which are connected to the internal combustion engine or the electric machine. And they are going to be also kind of pushing the vehicle in the forward direction. And the braking force is going to oppose the motion. And braking could be done by the electric machine if we do the regenerative braking, or it can be done by the mechanical system as usual. So these are the forces that we are going to see in the longitudinal axis. So I will talk about the motion and this Newton's law of motion. Here, what we know is we have the net tractive force. The tractive force is going to be applied to the wheels which are connected to the internal, let's call it the plants, power plants, which are connected to the internal combustion engine, to the electric motor, or both of them. And in this figure, you see that here it is FTR and FTF. So it means that F traction forward, front, F traction rear. It is shown that, so this is an all-wheel drive. So you can have the traction at both sides or at just one side, depending on the vehicle configuration you have chosen. But this is the total tractive force in the longitudinal direction. And we are going to have resistances. So as I discussed with you, we are going to have resistances, and we will talk about these resistances also later, one by one. And these resistances will, in this case, we are, in this photo, we are climbing a hill. So all these resistances are opposing the tractive force. The first resistance, as we are going to learn, the aerodynamic drag. The second resistance is the rolling resistance on the surface. And the third resistance is going to be this one, the grading resistance. So there is going to be force in the opposite direction. And the difference between these forces, the tractive force and all the resistances, is going to give me the acceleration. So if I can create a net positive force acting on my vehicle, my system will accelerate. And if this net force is negative, my system will decelerate. And if this net force is zero, as I'm going to show in the next slide, my vehicle is going to just keep its speed. This is what it says. So here, this is the V is the meter per second, and it is the speed of the vehicle in the given direction. Here, what you see. This M is the mass of the vehicle. So if you weigh your vehicle, this is the mass that you are going to see. And this delta is the increase of the mass due to the rotating bodies. Because if you want to accelerate your vehicle, maybe I have a small vehicle, I don't know if you can see it here. So if you want to accelerate your vehicle, you need to accelerate the total mass. That's for sure. For example, if your vehicle was flying, you need to accelerate all the mass. This is the M. On top of that, it has some wheels which are rotating. So these wheels has to have the also inertia, rotational motion, and you also need to accelerate these wheels. So that you need to give them the rotating motion. And moreover, we are going to have other rotating components within the vehicle. And to be able to, so it means that your effective mass is not going to be same as what you weigh the vehicle, but your effective mass is going to increase due to the rotating masses. And we need to include that into the mass. Therefore, we put here a delta. I will talk about how we calculate the delta. So we don't need to have a perfect calculation of delta, but you need to know that what you weigh, the mass, the linear mass of the vehicle and the accelerating mass of the vehicle are going to be different, since we need to also accelerate the rotating bodies. So as I said, the tractive force can be positive and negative. This is what plant generates. It can be on the front wheels, front axle, or the rear axle. So it depends on the vehicle. This can be both tracting and braking force. This resistances are the aerodynamic drag and the rolling friction. So they're always against the motion because they are the friction. And we also have the grading resistance, which can be positive or negative depending on the slope of the vehicle. So a float is actually this part, how you define the load. In electric vehicles, we are going to also include the resistances into the load, and we are just going to look them as one, but you're going to accelerate the system. And it means that actually in this case, if we separate them, this is going to be the float, this is the work that we are going to do, and this is, or we can also consider both of them together. As we said, if there is a net force, the system will accelerate. If the net force is negative, the system will decelerate, and there is no net force, the system will keep its speed. And you will see in this course, we will always look into the forward motion. All our vehicles are going to just move forward. We are not going to look into the backward motion. So therefore, this will be the case if the speed is positive. So when we come back for the vehicle resistances, we call them resistance because the first two is real resistance. They are going to resist the motion. And the third one can resist the motion or can help the motion, but it is also called the resistance. And you are going to see in this course, we're always going to assume that we are climbing a hill, because going downwards is not a big issue for the design. Of course, your brakes may be overloaded, but other than that, it is okay. But if you design a vehicle, you need to make sure that it can just climb a given rate, is able to climb a given angle, which you see here, this alpha angle. So therefore, when we talk about the grading or the grading resistance, it will be also always a resistance, because we will look into the worst case, and the worst case for the traction system is the climbing slope, not going hill down, but uphill. And this resistances total are, as I said, the rolling resistance, aerodynamic drag, and the grading resistance. So in the next slides, we are just going to look into all these resistances one by one. And once we are done, I'm just going to show you how we can calculate this delta and how we can estimate this delta, what this delta means. So the first resistance is the rolling resistance. So we have the wheels, and if you just want to move forwards, in this case, the vehicle is going into that direction. Here you see the moving direction, and this is just one wheel. And this is the weight normal load on one wheel. So because the whole load is going to be distributed among the wheels, assume that this is the normal load given on that wheel, because usually depending on how you drive and if you are taking a curve, or if you're accelerating or decelerating, the load distribution on the wheels are going to be different. But assume that we have the assume that we have some weight or some normal load on one wheel. And if we try to move in the plus x direction, let's call it it's the x direction, in the moving direction, the wheel or the surface or both of them are going to deform just because of this motion. So you try to move something in that direction. And due to this deformation, here you see the deformation on a hard surface. The surface is hard. In this case, the tire is deforming, more or less, as you can see here. And in this case, it's a soft surface. The tire is not deforming, but in this case, the surface is deforming. So you are going into the surface. This is how you can think. So in this case, since this was the normal load, here the center of load is shifted. The reaction force is shifted. And here, for example, the reaction force is shifted with an amount of A, and here it is shifted even more with an amount of bigger A. And due to this shifted reaction force, we are going to have some torque created in this center. And this torque is trying to just opposing the direction, the moving direction. And in this case, of course, this P is going to be same as the normal load. But this A, how much deformation we have, is going to depend on the tire, and it's going to depend on the temperature, pressure, and also the road surface. So it's going to change with many environmental effects. And this is going to create a torque in the reverse direction. And this torque can be just calculated times P times A. Here, as you see, the P times A. You don't need to know about it. At the end, we are just going to use one coefficient for that purpose. And this is going to be the torque. And if we want to calculate the force that we have, the braking force or the resistance force, we just need to divide it by the effective radius. Now the effective radius is also changing as the ground or the tire are deforming. So therefore, we are going to see a reverse force acting on the wheel, and this reverse force is going to be the rolling resistance. It is there because of the rolling motion, and it is going to be always opposing the direction of the motion. Here, this cosine theta and cosine alpha is here because this normal load on the wheel is going to change with the slope. So if you're on a no slope surface, the whole weight will be distributed on the wheels. But if you are just climbing a hill, it means that on the surface you will have less P. So therefore, you also need to include here the slope of the road. So how much M you are going to have here, M times G times cosine theta. And the total rolling friction is going to be a function of that, M times G times cosine theta. And this can be, this A over RD can be defined as the coefficient of the rolling resistance. And you don't need to know P, A, or RD, anything. But normally what we do is we use the coefficient FR, the rolling resistance coefficient, to calculate the rolling resistance. The big F is the rolling resistance force. FR is the rolling resistance coefficient. And it's going to depend on the mass of the vehicle times the G times the cosine theta. So how much weight you have on the wheels. It's going to depend on the weight on the surface. So this FR has different values, and as I said, it will change depending on tire material, structure, temperature, pressure, tread geometry, how the surface is formed, the road and the road material, if there's a liquid on the road or if there's an ice on the road. It will change with many things, but in this course, we are just going to use some constants to define this rolling coefficient. The rolling coefficient, some values are given here, but maybe here it is important. For the electric vehicles, we also use some low resistance tires, or we try to use low resistance tires. So this FR can be as low as 0.01. Usually it's around 0.01. Here you see also some rolling resistances on different roads, and also, for example, on rails, the rolling resistance decreases a lot. On sand, it is much higher, and so on. But usually in our course, we are going to use a rolling resistance around 0.01. We will assume that if we have an electric vehicle, most probably we have a good tire or high efficiency or low resistance tire. But what you need to know is this value will change with everything. For example, there are some definitions trying to include this FR as a function of a constant times this as a function of the speed. And here this Fs and F0 will change also with the tire pressure. So as most probably, as you know, a tire pressure is very important for the resistance on the tire. And if you have a high pressure, you will have less resistance. If you have less pressure, you will have high resistance. But this is not always the case, because we will talk about it later when we talk about the controllability, maybe. So the tires will deform differently. So it doesn't mean that if you decrease the pressure that your contact surface with the road is going to be higher. But usually the tires, when you put pressure, so they will just go like that. But when you just reduce the pressure, most probably they will just maybe have a hole in between, so they don't touch the ground. So it depends on the tire as well. So if you want to calculate this FR as a function of the speed, you can also use this equation. So these are just approximations, and it is fine for us. But as I said, in this course, we will most probably use a value of 0.01 or 0.015, and we will be happy with that value. So that was the first resistance, the rolling resistance. The second resistance is the aerodynamic drag. Because of that, you need to move the air, so you need to replace the air with the car. And this is the aerodynamic behavior of the systems. And you know, all the mobile applications, you need to be careful with the aerodynamic design of the system. And when it is a car, most of the time you need to be very careful of how you design the body of the car, because in total 85% of the total drag, the resistance, aerodynamic resistance, is due to the body shape. So it will include the basic body shape plus the tires and the wheels, how the air is going to go from these sides. And 10% is the skin drag. So like these mirrors, windows, and other antennas of the things. And 5% is the radiators here and what is happening under the vehicle. So when we talk about the aerodynamic drag, it is an important design criteria. So you need to design your vehicle accordingly so that our system has less drag. So once we have the vehicle or any mobile application moving parts, this FV, the W stands here for the FW, W stands for the wind. Aerodynamic drag, it can be calculated as a function of the density of the air, because you are going to move this air. So it depends on the density of the air. Frontal area of the vehicle, so what you see from the front side of the vehicle. Then CD is the coefficient of aerodynamic drag. We are going to discuss how this value changes. Coefficient of the aerodynamic drag times the speed square. So vehicle speed in meter per second plus the headwind, if you are having a headwind. In this course, we will also, we won't assume that we have any wind. It will be a still day for all semester. But if we assume, we will always assume the headwind. So it is just against the car motion. But keep in mind, if there is a crosswind, not directly coming with the 90 degree to the vehicle, but coming from different angles, it is going to affect the CD differently. So this CD is just for the headwind or the forward motion of the vehicle. If the wind direction changes, this coefficient of aerodynamic drag is going to change. But we don't care about it in terms of this course, but just know that we will assume that if we assume any wind, it will be a headwind, but most probably we won't assume any wind. So this is the aerodynamic drag calculation, so the resistance due to the aerodynamic drag, 1/2 times rho times frontal area times coefficient of the aerodynamic drag times the speed squared. So it means that if you go at low speeds, this is not a big issue because it will increase with the square of the speed. So the aerodynamic behavior becomes more important as the speed increases. So each vehicle, once it is designed, it's going to have a frontal area value and the coefficient of aerodynamic drag. And these depends, the coefficient of the aerodynamic drag highly depends how you form the vehicle, how you have the vehicle type. As you see, it is a rectangular type to more like a teardrop type. As you see, the aerodynamic drag coefficients are decreasing. It starts from 0.5, 0.7, and it decreases to 0.15 to 0.20. How much it can decrease is that if you have a teardrop with an aspect ratio of 2.4, because aspect ratio is also important, the sizes of these dimensions, and then this coefficient can be as low as 0.04. So depending on the type of the vehicle, because the number of the passengers is also important, or how much load you can put is also important. How the wheels, how high they should be also important. So depending on a type of vehicle, you need to design your body according nicely so that you will have a low aerodynamic resistance. So I have just found it from Wikipedia. There were some shapes and they were giving the drag coefficients. So the shapes are moving, or the wind is coming from that direction, from the arrow direction. So as you can see, actually, the side looking to the moving direction is important. Also, the side not looking into the in the backward direction is also important, because the sphere and the half sphere, they have different drag coefficients. And also the cube or the long cylinder or short swept cylinder, they have also different aerodynamic coefficients. So most of the time, the small cars tend to have a high drag coefficient than a longer car. This is what you can see here. So as it is shorter, it is harder to design to have a low drag coefficient, and as it gets longer, it will be easier to design a vehicle with a low aerodynamic drag coefficient. Maybe later for your projects, you will see that you will check the drag coefficients of different vehicles. And I think this is important. This American football ball makes sense, maybe because it looks like a tear shape. So maybe it has a good aerodynamic characteristics if you can throw it in the right direction. So here the idea what I'm showing that is not only the face or the frontal area in the moving direction is important, but also how the back part of the vehicle looks. It is also important, because maybe here we can see there should be some, because the air is going to enter from here, and air can create some turbulence at the back of the vehicle. And if we have a turbulence at the back of the vehicle, then it means that we will also have a high aerodynamic drag. So frontal area is important, but also back of the vehicle is as important as the frontal area or frontal shape. Let's put it like that. So previously I found a report. You can just check this report. It is still available online. So they were comparing different electric vehicles. So Chevy Volt, Mercedes-Benz, Nissan Leaf, Tesla Model S, and Toyota Prius. And they were comparing their drag coefficients, frontal area, and drag coefficient times the frontal area. So first of all, what you see is these vehicles are quite good drag coefficients: 0.29, 0.3, 0.32, 0.24, and 0.26. And as you see, the Tesla has a very good coefficient, also Prius and Chevy Volt has a good coefficient. And moreover, the frontal area is also important. But the frontal area is a little bit tricky because as you make the frontal area smaller, then you also cannot see outside. So there will be a comfort related problem and security related problem. So you should be able to see what is happening outside. So that's why there is a minimum. So you cannot really decrease it much further. And all these vehicles have the frontal area of 23.7 square feet. So it's around 2.2 meters square and around 2 meters square, the frontal area. And the multiplication is going to give you values around 0.6 or around 0.6 meters square, these both of them. But if these are what we have, the new vehicles, and when we compare it with the vehicles that we had earlier, and it will come in also in the next slide. So this EV1, the vehicle that we were discussing in the previous lecture, has a direct coefficient of 0 to 1. And XL1, I'm going to show its photo in the next one, it is going to have a direct coefficient of 0.90. But these vehicles are not, maybe I just show them, come back later. So this is EV1, it's a smaller model, I suppose. So it has a more or less a teardrop model, tear shape. And the windows are kind of low so that they decrease the frontal area. And this is XL1. XL1 means L1 was a 1 liter vehicle. So it was using just 1 liter of benzene or oil to travel 100 kilometers. And L1 was just for 1 person and XL1 is for two persons. So that's why it is called XL. So it is a bigger version. And as you see, all these vehicles have a similar shape. So the frontal area is reduced and the wind can flow easily. And even in this XL1, you see that they replaced the side mirrors by a camera. It doesn't have a side mirror. Anyway, so I will come to that. Maybe first I explain this. And in the same report, as I showed here earlier, they are also discussing how the direct coefficients are reduced. And they say that if you want to have an efficient driving, you also need to make sure that your shape is correct. And you need to have a flat underbody so the air can flow without any resistances. And here it says that most of the grills, so where the air has to go in for the cooling, is closed so that the air is going to flow from the upwards. It says that from the outside, it looks like a regular car, but there won't be much ventilations or much air going in, just a little here, the air is going to go in. And in the Toyota Prius, they fill the gaps at the bottom so that it will have a smooth airflow. And in the Nissan Leaf, for example, they make the headlamps here in a like buggy style. So, but it is not to make it look different, but it is more or less related to the aerodynamic drag. So you need to make sure that you have the right design. And so, as I said, this Tesla Model S and Model X, the coefficient around 0.24, the Prius also, but we have other examples, 0.21, 0.2, 0.9, depending on the application. So the electric vehicles also try to reduce the aerodynamic drag coefficient so that the system will be more efficient. Being more efficient is very important in terms of range because we have a limited amount of battery on board and we need to be as efficient as possible so that we can travel longer distances. And as you will see later, also the aerodynamic drag is our trouble at high speeds. And usually the electric vehicles have problem reaching high speeds. Or if you want to reach high speeds, you need to really put there a big motor, a big electric motor. So therefore, we will come to that later, that the aerodynamic drag is going to be important at high speeds. So this is XL1 and this is EV1. As I said, they have really good drag coefficients, low drag coefficients. I have driven XL1. And this car you don't want to drive, I can say. It's a zero comfort, maybe. And it is very weird to use cameras as the side mirrors, and you don't see much. There is very limited view. but it is a concept vehicle, and maybe one thing that you see is in both vehicles, the common thing, the wheels are closed, the back wheels are closed so that they have a low aerodynamic drag. But we have some winners in terms of aerodynamic drag. These are the solar cars, so it's going to move from that direction. So as you see, it has very few frontal area, and the driver can see from that much space, and this is also closed. So it means that we need to decrease the aerodynamic drag as much as possible, but still we need to give drivers some window opening to see, and we need to make sure that the car is still drivable. And so there's one vehicle on the roads, it is like 2 years, 3 years from now. So maybe you just go and read this review, or you can just check it by yourself. So when I see this vehicle, it makes me scared of the aerodynamic drag. So one question for the next lecture is, what is the coefficient of drag of this car? So what can it be? This is one question. Actually, when we just checked what we have seen earlier, so most probably it is something, a van body style, it should be around 0.5 and 0.7 drag coefficient. And you have seen that Teslas and other electric vehicles, they have more or less the values around 0.2 and 0.25. So this vehicle should be, I suppose, around 0.5 and 0.7. And this is what I'm going to ask in the beginning of next lecture. What is the drag coefficient of this vehicle? And also it has a very big frontal area. Okay, so the next we learned about the rolling resistance. Then we learned about the aerodynamic drag resistance. And now this is the grading resistance. This grading resistance is quite simple. mg, the gravitational acceleration, times the angle here. This is the alpha. And as I said, we will always think that our vehicle is going to climb back hill or on a level surface. We are not going to look into the case what happens if our vehicle is going downwards. So because it is a problem for the mechanical brakes, but not for the electric motor. Not exactly. So before we continue with the vehicle the other discussions, I just want to discuss with you what is this 31%. In the roads, when it comes to slope, it says it is 12% slope, 10% slope, 8% slope. It gives you different percentages, but this percentage is not that angle. So otherwise, 31 degree will be too much. So it is defined as how much, if you run 100 meters or 100 kilometers, if you go straight 100 kilometers, how much rise you will get. If these are same, so this is rise over run times 100 is going to give you this percentage. So for example, if this is the case, for example, it's 100% slope. If you rise for 100 kilometers going straight for 50 kilometers, then it is a 50% slope. Maybe I should use meters as the value. It is a 50% slope. So it means that here the angle, if it is 100% slope, the angle is going to be 45 degrees, and 50% slope, the angle is going to be less than 45 degrees. This is how the slope defined. And maybe you have been to California or other steep places. In California, there are really steep roads, extremely steep. And in this road, most probably it is not allowed to park in this direction, but you need to park just sideways in this part. And I do remember there were some roads that you cannot even want to walk upwards, like that. For example, here it is a grade of 31.5% gradient. It is given like that. So maybe before the next lecture, you can also check what is this angle. What should be the angle here? So obviously it is not 100%. It is not 45%. It should be less than much less than 45%. So what does angle mean? 35% gradient is too high. And what is the alpha in this case? This is another question for the next course. And let's see. Okay, so when we sum up what we have learned, anyway, I need to just finish the lecture slowly. we know that we are going to have the tractive force. This is what we will discuss in the lectures, how much tractive force we can get on the tires. So this is the tractive force on the front wheels. This is the tractive force on the rear wheels. And if we have an all-wheel drive, we need to add them up. If you have just a front-wheel drive, then we will have just the first one. And we need to get rid of or minus the resistances. The rolling resistance at the front tires, rolling resistance at the rear tires, and aerodynamic drag, and degrading resistance. In this case, we have also divided the rolling resistance at the front wheels and the rear wheels, because the total weight distribution between the front wheels and the rear wheels can be different. But most probably, in terms of this course, we are going to assume a constant weight distribution or a homogeneous weight distribution between the front wheels and the rear wheels. But the problem with this load distribution, how much M that I'm going to have on the wheels, here, for example, VF and VR, they will also change throughout the operation because they depend on the acceleration of the vehicle. So the resistances are defined, the rolling resistance, aerodynamic drag, and degrading resistance are defined here. So when we just look into the resistances on a level surface, so it means that this part is zero, there is no grade on this case, then it means that we are going to have the rolling resistance plus the aerodynamic drag. In this case, we assume the car CD is 0.3, so it's a little high. For electric vehicles, we have it a little small, but frontal area is 1.5 meters square. In the newer vehicles, we used to have a bigger frontal area. Kilogram is 100 kilograms, and FR is 0.050. So it is a okay vehicle. And in this case, if you want to accelerate until 160 kilometers per hour, this is how the rolling resistance changes. So it is the dominant resistance until the 30 kilometers per hour, or even 40 kilometers or 60, or let's come to here. So until 60 kilometers per hour, rolling resistance is high. And the second curve is the aerodynamic drag, how much aerodynamic drag that you are going to have. So it means that the aerodynamic drag is going to be very low at low speeds, but it is going to be extremely important at the higher speeds. And the rolling resistance are going to be important at lower speeds, and it is going to be much less compared to the aerodynamic drag as you go to the higher speeds. So therefore, if you want to increase the maximum speed of your vehicle, then you need to really make sure that this aerodynamic drag is in control. Maybe I will just stop here. It has been a long lecture. In the next lecture, we will talk about how we can create attractive effort and how we can later also calculate this delta, what this delta means. So I will just stop sharing, open the chat.